Okay. So, the last lecture we have discussed the line integral of a function of complex variable z and integral c f z d z, which we have defined as continued line integral that if a curve C is a curve whose parametric equation is given as x t plus I times y t, where t ranges from a to b and C is a smooth piecewise curve, and function f, which is defined at continuous, defined at each point on the curve C, then integral C f z d z. This is the limit of the sum sigma f of x I k into delta z k, k is 1 to n, and the maximum of this mod delta z k goes to 0. So, if this limit exists, we denote this by integral f z c z, and when C is a closed contour, then we use the notation circle. For a closed curve, we use this integral C f z d z as this. Okay. And then we have taken up one example that to evaluate this integral real part of z square dz along the path C from the point 0 z naught is 0 to the point z, which is a 1 plus 2 plus 4 I, where C is in three ways is defined. One is the line integral, the line segment, C is the line segment joining the points z naught to z, and in that case we have seen the value has come out to be, the value was integral, the value of this integral we have computed, because it is a curve, this is line and here is 0, this is the point z 2 plus 4 I. So, basically this line becomes y is equal to 2x, the line is y is 2x, and then x will vary from 0 to 2, and after computing the integral we have seen the value of this integral was coming to be minus 8 1 plus 2 I. In the second case, so this I because we have done it already. Okay. Second case where C is the x axis, C is a x axis from 0 to the point 2, and then vertically to the point 2 plus 4 I. That is, this is our point 0, here is 2, this is the path, here this is 2 plus 4 I. So, we are going along with this, along this. So, basically C here, C is C1 union C2, two curves are there, where the parametric equations of C1 and C2 are as follows. C1 you can write it, the equation, because along the path C1 what happens is the x equal to t by 0. So, z1 t, which I am writing for C1 as t a t plus I times of 0, where t varies from 0 to 2. Okay. And then if we substitute all these things, the value of the integrals that also we have taken, the value of integrals along this path was coming to be 8 cube by 8 by 3, 8 by 3. This was the value along C1. Then C2, C2 is the path vertically this. So, x coordinate is 2. So, Z2t is 2 plus y is varying. So, 2 plus IT, where the t ranges from 0 to 4. Okay. So, what happens in the integral, when you go for the integral, real part of z square dz by dt. So, here z is this equation d2z. So, dz2 we will write along this path. So, we get real part of x x square minus y square, x is t, x square minus y square dz2 by dt, and then t varies from 0 to 4. So, that will come out to be 0 to 4, x is 2. So, 4 minus t square dz by dt, dz2 by dt is, this is 0, this is 1 only, that is I only. So, it is I dt. So, it will come out to be this I dt, and when you compute this value for this, the value will come out to be minus 16.3 by 3 I. So, C1 along the value is coming this, C2 along, therefore, along the second path, along second, the value of the integral is C1 union C2, that is 8 by 3 minus 16 by 3 I. Earlier the value was something different, it was minus 8 1 plus 2 I, and here is, and in third case also, when you take the path is a curve parabola, the path, if you remember, this was the parabola, C is the parabola, y is equal to x square, joining these 2 points, joining z0 to z. So, in this case, the parametric equation of the curve C will be xt. If I take t x as t, then y becomes t square. So, I t square, and t varies from, because it will go from 0 to the point 2, is it not, 0 to 2. So, it is 0 to 2, and then find out the dz by dt and other. So, if we take the dz by dt, this comes out to be 1 plus 2 I t dt, and then real part of z square is x square minus y square, x is t, y is t square. So, minus t4 this is, and therefore, the integral of this along the path C, real part of z square dz is equal to integral t square minus t4 1 plus 2 I t dt, and t varies from 0 to 2, 0 to 2. So, if I compute this value, the value will come out to be minus 56 by 15 minus 40 by 3 I. So, what we conclude is that this is our 2 points z0 and z is 2 plus 4 I. We want the integral of this function real part of z square dz along the path C, where the C varies. In the first case, it is a straight line joining these 2 points, this is the first path. In the second path, we are going along this and this is the second part, and third path will be like this, a parabola. So, in all the 3 cases, what we are seeing, the values are different, they are not coming to be the same. It means the line integral of the function f, though it is continuous function, will exist, but it depends on the path of integration. So, the important result is the line integral depends on the path of integration. That's so our aim is to, because once it depends on the path of integration, then the problem is there, because we cannot take this value or that value as our subsequent work, because it depends on the path of integration. So, we have to identify certain condition on the function, so that when we get the integral should be independent of the path. It should not depend on the path. So, once you have that type of the function, all the condition on the function, so that it is independent of path, then this value will be taken up for our subsequent work, and that is the one. And in this consequence, the Cauchy integral theorem plays the vital role. In fact, that is the key point from where you can justify that the integral will be independent of path, provided certain conditions on the functions are satisfied. Okay. So, let us see. Now, prior to the Cauchy theorem, little bit just one more concept about the ML inequality, and that ML inequality say what is this ML inequality? If f is integrable on a curve C, let C be a piecewise smooth curve, whose equation is, say suppose zt is xt plus I by t, t varies from a to b is given, whose equation is this given. Okay. And let f be a integrable function on C. Integrable means it is continuous basically. So, once you take it continuous, T will give the guarantee that it is an integrable function. However, there are some functions also which are even not continuous, but it can be integrable. So, let it be integrable functions on it. And let suppose let the length of the curve C be L, okay, BL, let length of the curve BL, and function f is such which is bounded by M, bounded function for on C, that is at each point the function is well defined, but the value of the function does not exceed by some constant, say M on C. Then this ML inequality says that modulus of the integral fz dz over the curve C is less than equal to M times L, and this is known as the ML inequality. Okay. So, proof I am just deleting, because the proof based on the definition of the line integral fz. When function f is integrable, then we can write it this in the form of the this way, in the form of this series, and then when you take the mode of this, basically mode of this is less than equal to this, which is less than this M, and get the mode of dz is nothing but L. So, this is very now. If you the arc length of the curve C, is given by this formula, which is also used, will be used mod dz over the curve C. So, these two things will be needed in futures whenever we go for. Okay. Now, let us come. We have discussed the domain. Domain is an open connected set. Now, for the Cauchy integral theorem, when we consider the function f which is analytic in a domain, we do not simply take the domain. We do not simply take the domain. What we do, we require something more, and that we has a concept of simply connected domains, which is required for this. So, first is domain is an open connected set. Is it not? In the complex plane, this is a domain. Then simply connected domain we define the simply connected domain a domain in which any simple closed curve, a domain in which any simple closed curve can be shrinked to a point without leaving the domain. So, what is the meaning of this? Suppose this is a domain D. We say this domain is a simply connected domain. If we picked up any closed curve C, any simple closed curve C, and try to squeeze it, and if it shrinks to a single point to a point without leaving the domain, means no times these while shrinking the points are outside of the domain, then such a domain is said to be a simply connected domain. For example, our circle mod z less than 1, this is a simply connected domain, is it not? Simply connected. Half plane, real part of z is greater than 0. Real part of z is greater than means x, this is the plane, x is real part, sorry, I am sorry, this is the imaginary part of z is a. So, this is imaginary part of z is greater than 0, because this is a positive part, and real part of z is this one. This is the real part of z. Okay. So, in this real part of z, if I bring it any closed curve, then it can be shrink to a point without leaving the domain. However, if we picked up the domain like this, suppose I take mod z 1 is less than mod z less than 2, then this domain is basically an analysis centered at 0 between the two circular disk circle between mod z less than mod z 1 and mod z 2. So, this portion is an analysis. Now, in this analysis, if we take a closed curve, then always you cannot get the condition to be satisfied, that is we cannot always shrink to a single point without leaving the domain. For example, if I take this domain, in this domain, if I take this circle and then try to shrink it to a point, then as soon as it comes to this boundary, up to here there is no problem, but as soon as it crosses the boundary, these points are not available in the domain, because this is the only domain. So, it cannot be shrink to a single point. However, if we take this curve, it can be shrink to a single point. So, it does not mean that domain is a simply connected domain. What the condition is? Any simply closed curve. The condition is any simple closed curve can be shrink to a point without leaving the domain. So, that is why this is not a simply connected, is not a simply connected domain. Similarly, a domain of this type, if I leave these two holes and only this portion are taken, then this is also not a simply connected domain, not simply connected domain. So, such a domain which are not simply connected domain are said to be a multiple connected domains. Okay? And then the domain which has a two boundaries be defined as a doubly connected, which has a three boundary, which has a triply connected domain and so on. So, in general we define a domain as a p-fold connected domain, p-fold connected domains. P-fold connected domain, a bounded domain D a bounded domain D is said to be p-fold connected domain if its boundary consists of p close connected set p close connected set without common point. Okay. Say for example, in this way, this portion I am not taking, this is out. So, this is not a simply connected, but if I join this thing like this, then once you start the moving from here going towards this and then coming here, finally it comes here and like this. Now, this becomes a simply connected domain. Similarly, when you go from here up to here and then come back from this, going this and coming like this way and again this side. So, this will be again it means this domain D is divided into two subdomains D1, D2, which are simply connected domains. So, it will be a doubly connected domain. This is the doubly connected domains. Now, here you remember there is a one hole in that. So, if a domain has a single hole, it is a doubly connected. If it is two holes, it will be a triply connected. For example, this, suppose we have these three holes, then again we can draw like this. Suppose we get this one, okay, and then like this. So, we can get this figure, okay. We can go through this way and then three domains we are, yes, 1, 2, 3. So, 3 we are getting this domain which is simply and two holes. So, this will be a triply connected domain. Okay. So, that is very important for this. Okay. Now, come to our main result, which is the Cauchy theorem. Now, Cauchy's integral theorem. The Cauchy integral theorem says if f z is analytic, if f z is an analytic function, in a simply connected domain, in a simply connected domain D, and the derivative f prime z is continuous and the derivative f prime z is continuous in the domain D, in this domain D, then for every simple piecewise smooth closed curve C contained in D, then for every simple piecewise smooth closed curve contained in D, the value of the integral C f z d z will be 0. So, what this shows? This shows that if a function is analytic in a simply connected domain D, means function must be analytic, as domain should be simply connected domain, and this is an extra condition he has chosen Cauchy, but without even these conditions one can prove that is proof is given by the Gorsuch, and then even this condition can be dropped. The reason is means the function is analytic, as I told earlier also, then all of its derivatives will exist. So, all derivative exist means automatically the derivative f prime z will becomes continuous. So, basically this condition need not be required in proof, but that proof itself is very wrong. So, Cauchy did it, Cauchy used this restriction and then proved it with the help of the Green's theorem. So, what this says is, suppose f be a analytic function in a domain D and derivative is continuous, then if I pick up any closed curve C which is simple piecewise closed curve totally contained inside C and its point also, function is analytic at each point as well as inside C also continuous, then the value of this integral will be 0. Okay. The proof of this based on the Green's theorem. So, before going the proof, what is the Green's theorem is? Let us see first the Green's theorem, because that will be required in proving this result. Green's theorem said let f and d, let p and q, p which is a function of x y and q which is also a function of x y be any continuously differentiable function, any two continuously differentiable functions, means p and q both are continuous, they are differentiable, partial derivative with respect to x and y of p and q exist, continuously differentiable function inside a region R, inside a region R whose boundary C gamma is a closed curve, then this theorem says the value of this line integral of the function p dx plus q dy, this is equal to the double integral of the function del q over del x minus del p over del y dx dy over the region R. So, this is our region R, R is this region, boundary is this, C is a closed contour covering the R, function p and q both are continuous, possess a continuous partial derivative at each point on this domain D, then the line integral can be transferred into a double integral with the help of the Green's theorem. So, we will make use of this result in establishing or in proving our Cauchy theorem. Let us see. So, proof of the Cauchy theorem. Proof of Cauchy integral theorem. Let us suppose f z is u plus iv, where u is a function of x y, v is also a function of x y, and f is given to be analytic and continuous. So, u and v both are analytic and continuous. Consider integral f of z dz. Now, when you substitute f z is u plus iv and dz equal to dx and dy, then it can be break up into two parts, as we have seen in case of line integral u dx minus b dy plus eta times integral v dx plus u dy. Okay. Now, apply Green's theorem. Because function is analytic, derivative is continuous. So, u and v both are continuous functions, possess a continuous partial derivatives, and C is a closed curve. So, the region, this is your C, this will be the region R. So, if we apply the theorem, Green's theorem, then this can be written as the double integral over the R, del q that is equal to p dx plus q dy. So, the integral is del q over del x. So, minus del v over del x, then minus times del p over del y, del q over del x minus del p over del y, okay, dx dy, then plus I times double integral r. Here also this is del q over del, so del u over del x minus del v over del y, dx dy. Okay. Now, since the function f z is analytic, so its real and imaginary parts, its real and imaginary part will satisfy CR's equation. So, u and v are the real. So, by CR's equation del u over del x is del v over del y, del u over del x is del v over del y. So, second part vanishes, that is del u over del x is del v over del y, and del u over del y is minus del v over del x. So, first vanishes. So, this implies that integral C f z dz is 0, and that is proven. Okay. Now, Cauchy has proved this by using, but the Cauchy-Gaussian has dropped the idea of that continuity, and then also he has proved the thing. So, we are not interested in that, we just go. Okay? That is the proof. Now, let us see a few example which will show the direct application of the Cauchy integral theorem, but somewhere we also see it does not contradict the Cauchy integral theorem, though the integral is coming to be 0. Let us see the example. Suppose I want the integral of the function sec z dz over the curve, say C, which is mod z equal to 1. Okay. Now, what is sec z? Sec z is 1 by cosine z. So, cosine z becomes 0 if z is the point plus minus pi by 2, is it not, plus minus 3 pi by 2. These are the point where it becomes 0. So, function is not well defined at this point, But if we look the circle centered at 0 with a radius 1, then all these points lies outside. Here somewhere they are lying, isn't it? So, function sec z is totally analytic inside as well as on the boundary of this C. So, this value, this is 0 because sec z is analytic inside and on mod z equal to 1. No singularity. So, by Cauchy integral theorem the value will be 0. Similarly, if we take the integral e to the power z mod z equal to 1, it is 0, and like this any analytic function if you picked up the directly value will come out to be 0. Then let us see some. Suppose I take the integral dz by z square. We wanted to evaluate it along the circle mod z equal to 1. Okay. So, write down the parametric equation of the curve. To the circle C is zt equal to e to the power I t, cos t plus I times sin t, mod z is 1. Okay. And t varies from 0 to 2 pi, one side open, other, okay, 0 to 2 pi, and that is okay. So, if we substitute it, then dz becomes I e to the power I t dt, and then twice I t 0 to 2 pi. And if I compute the value of this, the value will come out to be e to the power minus I t by minus I 0 to 2 pi. Now, e to the power I 2 pi cos 2 pi plus I times sin, so it is 1, and minus this 0. So, basically the value will come out to be 0. So, value of this integral along this closed path is 0. This is the circle C centered at 0 with radius 1. The function, the value of this integral is coming to 0, but what is the function? Function f z square has singularity or not defined, we can say, because we have not introduced the concept of singularity, not defined at z equal to 0. So, function ceases to be analytic there. It means the function is not analytic. In spite of this, the value of this integral is coming to 0. Does it contradict the Cauchy theorem? No, it will not contradict the Cauchy theorem, but the Cauchy theorem says if the function is analytic, then the value of the integral along any closed path must be 0. But it does not say the other way around, that if the integral of the function is 0, then whether the function is analytic, that does not the conclusion, this does not the meaning of the Cauchy theorem. That is, Cauchy theorem is only one way is true, that if the function is analytic, then the integral of the function along any closed path in a simple domain will be 0. That is, the analyticity is the sufficient condition, but not the necessary condition. So, this shows so this example shows that this example shows that the f is analytic is several other than s, that the analyticity of the function f z in a simply in a domain D is sufficient condition is a sufficient condition for integral f z dz along the closed path C to be 0, but not necessary. Okay, this is the one. Now, let us take the example, another example. Suppose I take the curve integral, evaluate this integral dz by z along the path mod z equal to, say, mod z less than half, counter close, less than half and less than 3 by 2. Let us take this. That is, we are taking an annulus centered at 0 with a radius half and 3 by 2. So, this is the portion. C is a curve. C is any closed curve. We are choosing any closed curve. This is our closed curve C. This is C. Annulus boundary. Okay, this is the domain and C is this boundary. Lies in this. C lies. No. C, where C is a closed curve lying in the annulus. Annulus in this annulus. So, unit circle lies in the annulus. Now, what is the value of this? Let us see. So, let z is equal to e to the power I t, and sorry, r e to the power I t, because you take the any r e to the power I t, then what will be this? Dz becomes r e to the power I t into I. So, integral t varies from 0 to 2 pi, because entire circle, and then this becomes dz means I r e to the power I t, z is r e to the power I t and dt, is it not? And then t is 0 to 2 pi. So, what you are getting is this is coming 2 pi I, is it not? And here the function f z, which is 1 by z, is analytic. Inside the annulus, 1 is less than this, less than 3 by 2, half, less than mod z, less than 3. So, function is analytic in the domain. This is our domain where the function is analytic, but and C is also closed, and C is also closed curve, Still the value of this integral is not equal to 0. Again, it does not contradict the Cauchy theorem, because we cannot conclude from the Cauchy theorem. The reason is all the conditions of the Cauchy theorems are not satisfied. What the condition of the Cauchy theorem is, the function must be analytic in a simply connected domain, but this domain is not simply connected, this is inside the domain D. So, is not so here D is not simply connected domain. That is why we cannot say the concept. So, so in the Cauchy theorem, what remark we can say, that the condition of the simply connected domain, the condition of simply connected domain D is quite essential in while applying Cauchy theorem, Cauchy integral theorem. So, that is must in that. Okay. Let's one more example. Let us see. Suppose I take the integral of this curve z bar dz. Now, this closed curve C is a circle mod z equal to 1. This center 0, radius 1. C is a closed curve. Now, if I compute the value of this integral, the value will come out to be t range from 0 to 2 pi, and that z bar is minus I t, dz is e I t, dt 0 to 2 pi. So, the value will come out to be 2 pi and dt is I, 2 pi I. So, value will come out to be 2 pi I. Now, here again the curve is closed, but the value is not coming to be 0. The reason is the region is that the function f z, which is z bar, is not analytic, in the complex plane C. In fact, this we have already seen that this function is only differentiable at 0 and nowhere else. So, it is not analytic throughout the domain. Therefore, whatever the closed curve we choose, the function is not analytic at all. Therefore, so this will okay. So, we get this so other thing. Now, okay, let us come to the slightly as we have told earlier that line integral, since it depends on the path of integration. So, there is no use unless we are sure that the computation of the line integral is independent of the path. So, for this the Cauchy theorem helps. So, what is the result is independent of path. What this says is, let f z be analytic in a simply connected domain D, and let C be any path joining 2 points Z1 and Z2 in D. 2 paths joining Z1 and Z2 in D. Okay. The path C lies totally in D. Then the integral f z dz along the path C, along the path C is independent of path. This line integral is independent of path of integration. And depends only on the endpoints Z1 and Z2 joining the curve, endpoints on the curve. So, what the meaning is, suppose D is a simply connected domain, D is a domain and F simply connected domain. F is a function which is analytic in this simply at each point in the simply connected domain. This is a curve C joining the point Z1 to point Z2. Now, this theorem says that if I integrate this function f z dz along the path C, then this integral will be independent of path. That is, if I take another curve, say suppose I take this curve C star, then the value of the integral along C and the value of the integral along C star will be the same, whatever the path is, whether you join this or this, whatever may. Okay. So, this result can be followed immediately from the Cauchy theorem. Let us take suppose 2 paths C and C star joining the point Z1 and Z2. So, when we start from Z1, go along the direction of this C up to Z2 and then come back to Z1. So, this will give a closed path. So, we get the closed path will be C union minus C star, because the order direction is reversed. So, this is the closed path. So, and the function is giving to be analytic throughout this domain. So, it is also analytic inside and continuous on this boundary also. So, integral of this function f z dz along C union minus C star will be 0. But this is the same as the integral C f z dz minus integral f z dz C star, because this minus, or we can write minus here and then minus C star. Then minus of this becomes the minus, because the order direction reverse means this will be negative value. Okay, so, we get this and this is coming to be 0. So, integral C f z dz minus integral along C star from here to here f z dz is 0. This implies integral C f z dz and integral C star f z dz both are same, both will give the same value. So, it is independent of the path, and that is one of the interesting result which is a consequence of the Cauchy integral theorem. Another consequence of the integral theorem is the second note. Suppose we have a 2 point z naught and z and a very zigzag path is giving, say, okay, just with a simple piecewise smooth curve is there. We wanted to find the integral of the function along this. Then instead of this, if we bring it to a path which is much simpler, then the value of this integral along this path and this path will be the 0, will be the same, and that gives the deformation of the path, that gives an idea of the deformation of path. Means we can deform the path, whatever the path is there, we can try to skew it to some, means this we can think that C is the deformed path of C star. Slowly we are just reducing, coming down, and so that C star and C coincide, and always in this process the integral will remain the same. Thank you very much. Thanks.